Greetings and welcome, friends. Today we're talking about composition of functions. Now, you've heard us talk about functions before, quadratic, linear, polynomial, and the like, right? And functions I've loosely defined as saying that there's exactly one output for every input, okay? And that's what a function is, all right? Exactly one output for every input. And what I've drawn here are four machines, if you will. If you imagine I work in a factory and I put some things in here and out comes the output from that machine. And each of these machines serves a different function, classic, in which they all do something different to what's put into them. All right, so for instance here I've got my classic x plus 3 machine. And let's just jump right into a little example with this. All right, so here's my f of x is the x plus 3 machine, meaning anything that goes into this machine gets added by 3. So let's say I wanted to, for instance, calculate what is f of 1. Well, I'd put 1 in here, and what would pop out? 4. Wow, it's amazing, right? So f of 1, mathematically speaking, would be 1 replace the x, right? And I add 3 to it, and I get 4. There you go. Not too shabby, friends. Let's say I plugged in, let's really try to break this machine, 7. 10 is going to come out the other. Man, input, output, right? We get the idea here. So I could write f of 7 would have equaled 7 plus 3, and that's equal to 10. Right? So you've seen this type of notation before with functions. I also could have represented this tabularly, right, as a table. That's just a fancy way of saying it. Where I could have said, right, when the input was 1, the output was 4. When the input was 7, the output was 10. Now, let's say, what if I input 1 and I got a 3 another time? What would your issue be with that? With this table. What if I told you f of 1 was equal to 3?
-1. The absolute.
Well, the issue is this is no longer a function because the input would have given me 2 different outputs, right? If I plug in 1, I should get exactly the same thing out of it every time. Otherwise, this machine is not qualified to be used in a factory, right? I want exactly the same product to come out of it every time. And if plugging in 1 gave me 2 different things and I don't know which it's going to give me when, that's no longer a function. That could be a relation, is kind of the more loosely defined relationship, right, sort of thing, equation that you can have, is a relation, and relations can have more than one output for every input, but not functions. Functions are like, no, anytime you plug in a 1, you get a 4 every time, all right? Todo de los tiempos, all right? Now let's actually, someone said, what would happen if we plugged in -1? Let's just see. What happens if I plug in -1? Ah, wonderful. I'd get 2. Actually, I want to scratch this over here. Right, that is not true because it would not be a function. So f of -1 would have been -1 plus 3, and I'd get 2, right? So I can plug in all sorts of crazy stuff here, right? What if I plugged in the square root of 2?
3 plus the square root of 2.
Yeah, so you might have thought that that would break my machine, but we actually had no problem with it. That would just be replace x with the square root of 2 and add 3 to it. I can't really add those. I might rewrite that as 3 plus the square root of 2, like Joey suggested. I like that idea. So f of the square root of 2 is just 3 more than the square root of 2. 3 plus square root of 2, right? So this function, is there anything I could plug into this function that would break it? Well, that would just be 3 plus pi, or pi plus 3. X would just give me x plus 3 back. That's actually an interesting idea. If I plugged in another variable, right? If I plugged in y here, I just get y plus 3 back, right? Sort of thing. So this function actually, I think, allows anything for inputs. What?
Not anything. It doesn't allow like a banana.
It would just be a banana plus 3. But okay, you're correct. In terms of numbers, this function allows anything. Now, if I'm talking about what kinds of inputs are allowed, I'm referring to the domain. All right? The domain of a function is the set of all possible inputs. All right, and I've actually seen domain listed a few different ways. So you might say the domain is the set of all x. You might say the domain is, I guess you could say negative infinity is less than x is less than positive infinity. You might say the domain is from negative infinity, non-inclusive, to positive infinity, not inclusive. So there's like actually a bunch of weird ways you can write this. And I'm going to try to have you be familiar with those over time as we use them all.
Can you go through the quiz or the test?
Sure. So that's the domain, is the set of all possible inputs. Now in our case here, it allowed all possible inputs from real numbers, right? So the domain would have been, right, all possible x, or all x values between negative infinity and positive infinity, right? So these would be describing the domain of that problem. Now the range, range is actually a math term that has two separate meanings in the domain of mathematics. You may be familiar with the word range regarding statistics. Does anyone know what the statistical definition of range is, or what it means? Yeah, the range in a set of data would be referring to the highest number minus the lowest number. Okay? The range in terms of functions is the set of all possible, can you guess it? Outputs. What? These mathematicians. So the range can be defined in kind of the same ways. Here the range would be the set of all y, all right, or output values, all right. That's the idea. So I could also write it in those other ways. Now, question, looking back at this problem, are there any outputs that I couldn't get? If I wanted an output of negative 10, what would I plug in? Negative 13. If I want an output of 27, what would I plug in? Positive 27. 24, right? If I wanted an output of pi, could I plug something in that would give me that?
No, you would just put it as
The decimals after pi, all right? I'm getting multiple concepts like that. If I plugged in pi minus 3 in here, I would get pi because the negative 3 and the positive 3 would cancel out, right? And that's why they were saying the decimals after pi, right? The non-3 part of pi, so the 0.14159, right? So it turns out for this function, its range is all possible values. There's nothing I could plug in here that would break it. So the range is everything, all right? So there's
infinity to
yeah, I could specify it like that as well. So I could say, negative infinity. Man, that's a sad looking.
It looks almost like a sad jellyfish.
There we are. So yeah, from negative infinity to positive infinity would be the range, right? So range is outputs. Domain is the set of all possible inputs. And in order for this to be a function, I expect that every one of these inputs will only give me one output. Now, would it be a problem if I had the same output twice?
Yes.
Now in this case, I believe there's a unique output for each of these. This is a linear relationship. But let's actually analyze another one. Let's look at this j of x machine. Example. Let's see, wrong color here. Yeah. So let's say I've got this machine here, j of x is equal to x squared. And let me ask you, I want to find the domain and range of this function. Well, let's tinker around with this a little bit first. What if I want to figure out what is j of 2, for instance? Well, that would be 2 squared, and out would pop a 4, right? I plug in a 2, a 4 would boop, plop right out of it, right? Now, thinking about domain and whether anything breaks this as far as an input, it's worth trying kind of like the typical troublemakers of numbers, right? So I'd be interested in what happens if I plug in a negative, for instance. So -1 all squared, you guys are all masters at that. What would I get? +1. Okay, so the plugging in a negative didn't seem to break it. Plugging in a square root? Yeah, let's plug in the square root of 2. Square root of 2 squared? Yeah, that would just equal 2. So it appears as though, yeah, it seems like everything would work. So if I wanted to describe the domain here, what would you describe it as? I don't know. Feel free to look around. So the domain would be from -infinity to +infinity. There's no value I could plug in that wouldn't come out of it. Now, what about the range? Actually, I'm not going to put parentheses in. What are the possible outputs for this? 0 through infinity. I can't get -1 out of this machine? Why not? Yeah, so the squaring is always going to give me a positive output. For instance, if I wanted to figure out j of -2, that would have been -2 squared. That's +4. Now, is this an issue right here? I just got the same output twice. Is this still a function?
Yeah.
It is. It's okay to get the same output multiple times. There can only be one input for any given output, though. Okay? So every time I plug in -2, I'm always expecting 4 to come out of that. All right? So the range, I believe Joey's correct. He said it's from 0 to infinity. The way you would write this, ready? What? Square bracket to close parenthesis. Now, what does this mean? I could also have written the range this way, where I would have said 0 is less than or equal to y, which is less than infinity. All right, the idea is that it could never equal infinity, because infinity is not a number, it's kind of a concept. So that's why the parenthesis is kind of like a not inclusive part. It didn't have the equal part, whereas a square bracket includes that point. Okay, so don't confuse this with an ordered pair. This is referring to the domain. This is referring to the range. Yeah. If, for instance, you had open parentheses there, that would mean 0 itself doesn't work. Everything after 0 would work. Question? Mm-hmm. So there's some domain and range. Now, in terms of functions, I just want to point out a couple other ways to represent them. All right. A relation in which there's exactly one output one output, O-U-T-P-U-T, for every input. And so far we've seen our functions represented in kind of the f of x, g of x format where it's written as an equation, all right? It's also possible to represent functions graphically. All right, so here's a graph. All right, you could have a table. You could have an equation. And you could also have an input-output chart. So I'm going to try to quickly draw what each of these look like. So a graph, table, and then the input-output chart is going to be interesting. So for a graph, yeah, I'll get there. For a graph, actually, let me draw this in green. Why not? Why not, shall we? Now, I've referred to as polynomials as functions. Now, graphically, I know that this is a function because for every input, there's exactly one output. Okay? Now, what that means is for every x value, there's only one y value above or below it. Okay? If I had, for instance, this, would a circle be a function?
No.
Because imagine on the crosshairs of the grid, if I ask you to plug in 1 and say 1's there, you wouldn't know whether it's positive this or negative that, right? There'd be two outputs for that one input. So there's what's called the vertical line test, whereas if it's a function, if for every vertical line you could draw, it's only ever going to hit at most one point. All right, so graphically that's what a function would look like. On a table, right, I could have a table like this, 2 and 3 and 3 and 5 and 4 and 7 and 5 and 9, right? So you could have a table, and as long as for every input there was one output, you're all set. So the inputs are the x's, the outputs are the f of x or the y, depending on what you have. An equation is when you have f of x equals something, right? Right, that's a function right there. And then an input-output chart. This is actually kind of a weird representation. This is when you have two kind of ovals, I guess. And then these are your inputs, and these are your outputs. And you'd have just like a list of numbers in each. So here's 2, 1, -3. Maybe my outputs are 8 and 10 and 7 and 14. All right, and for my input-output chart, what you would have is a relationship of arrows here. So this would be like if I plug in a 2, I get an 8. All right, if I plug in a 1, I get a 14. If I plug in a -3, I get a 10. All right, and according to this relationship, is this a function?
No.
Well, for every input, if I input 2, it's always telling me to get an 8. There's one output for that input. There's one output for that one. So there's exactly one output for each of these. So this is, in fact, a function. All right? Now, it would fail being a function if, say, I had this. What if 1 had 2 arrows pointing away from it? So that would be 2 outputs for one input. That would be a no-go. All right? Would this be a function? What if I had a 4 here? And what if that also pointed to 14? That's okay, right? Because the 4 always gives me 14, the 1 always gives me 14, there's no confusion. It's okay that they gave me the same output. But for each input, there was exactly one output that it gave me. All right, so that's kind of some different representations of functions. All right, and if it fails the vertical line test, or if there is more than one output for every input, then it's just called a relation. So a relation is actually just a relationship between numbers. It's a pattern or something to that effect. And it doesn't necessarily guarantee that there's one output for every input. Okay? So let's consider some more crazy things with our machines, these functions that we have. Let's say you're working in the factory, right? You've got all these machines in your factory, and you and your buddy, you're working late one weekend, the boss went home or whatever, and you're like, hey, I've got a crazy idea. A real crazy idea. All right? This is going to be crazy. Cray-cray even, right? Let's say that you're like, what I want to do is I want to take this machine, all right, our f of x machine, and I'm going to set this machine up so that immediately as something falls out of the f of x machine, it will fall into the h of x machine. All right, so like you're just like, let's just do something crazy here, right? So you have to build, of course, like maybe some sort of shelf to support this system. But the idea is that when something goes in here, falls out here, immediately goes into the h of x machine and comes out. Okay, so let's do some experimentation here.
Does it always have to be like x plus 3, or can that 3 be changed to a different number?
Yeah, this could be a different number if you have a different function. I mean, you can call it anything. Let's say I plugged in, I don't know, 6. Now, the moment you see it coming out of this machine, what was that number?
9.
You'd see a 9 falling into the h of x machine. And then the square root of 9 would become 3, right? Okay? So now, to represent this, all right, this is called a composition of functions, where I'm combining them, I'm composing multiples of them together. And what I would describe this as is h of f of x. Or actually, let's specifically do 6. All right? So this is read as h of f of 6. This is how you would read that. It's a lot of f's back to back. So I could just throw an O there to have a nice pattern, but that's fine, that's fine. So h of f of 6, if I want to calculate that, what that means is calculate f of 6 first. And what was f of 6 equal to? Well, 6 plus 3 is equal to 9. And now f of 6, whatever I got, is going to be plugged into h. Right? Just like we saw here visually, right? I plugged in 6, out popped a 9. 9 is being plugged into h. So let's figure out h of f of 6. I'm going to plug the 9 into h. All right, so that's 9, or actually maybe I'll just write that this way. H of 9 is going to equal the square root of 9, which is 3. And that would be the overall output from my combined machines, my composition of functions. Okay? Craziness yet? We getting crazy? So let's plug in a different value. Let's see if we can figure out what is h of f of, I don't know, negative 2. So what does that mean? Now looking at this, you take the innermost part, plug it into that. Then you take your answer and you plug it into that. All right, so you start from the inside and work your way out. Okay, is the idea. So let's calculate what f of negative 2 is. So that's going to be 1. And what's h of 1? 1. All right, so I plug in a negative 2, out pops a 1, and it falls immediately into the square root machine. Square root of 1 is also 1. Okay, not too crazy. Now question, do you think that h of f of negative 2 would be the same as if I plug the negative 2 into the h machine first? Is that going to be the same as f of h of negative 2? No. Well, let's calculate that. F of h of negative 2. So that would be if this machine was dumping into that machine, right? So what is h of negative 2? Be the square root of negative 2. And that would just be, well, we know it's imaginary, but as far as these machines are concerned, and our boss would be, he's like, what do you mean you just converted all of my negative 2 real numbers into imaginary ones, right? He wouldn't be happy about that. So right, that would just be I square root of 2. And then I'd have to plug that into the f machine, I square root of 2, and I'd get I square root of 2 plus 3. Right, or 3 plus I square root of 2 is probably the better way to write that. But we would just call that, uh-oh, I broke the machine. right? That would just be real bad news. So clearly, -2 was not within the domain of my h of x machine. All right? It's like you put a waffle in a DVD drive, right? That machine was not intending to have waffles put in it, right? And chances are, if a kid does that, they just didn't read the user manual, right? Or like, I think my wife's sisters used to put quarters into the CD drive of their car's CD player. Yeah, also not a valid input.
Fork and power outlet.
Fork in a power outlet. Now, I would question whether or not it breaks the machine. It would not be good for the user, though. So I just want to point out that reversing the way they're inputted is not necessarily the same. Now, let's suppose, have you guys seen a TV that also has a DVD player built into it? Or a VCR DVD combo? A TV VCR DVD combo, right? What if, now this is crazy, what if you and your friend, working late at the factory, you're like, let's take this whole machine and cram it into the h of x machine?
Why would you try?
Because your boss is gone. You're just like, let's do this. And like, so you're just like jumping up and down on the top of the f of x machine to try to cram it into that,
I would
right?
put the other one inside because it looks smaller.
Yeah, it does look smaller, but your goal is, I'm going to put this whole machine into the h of x machine. All right? So we're just getting crazy. We're like, all right, we broke one of them already. Let's just see what happens here. So let's do this example.
I don't like that. That's stupid.
So this would be h of f of x, meaning for the function h, I'm putting f inside it entirely, replacing all of its x's with whatever f of x was. All right? So what was h of x? That was just the square root of x, right? And what was f of x? X plus 3. So I'm cramming an x plus 3 inside of the h of x machine, and that would just be the square root of x plus 3, no parentheses needed.
So it didn't break it.
So it doesn't seem to have broken it. So we just invented a new machine, right? Maybe our boss will pay us extra on Monday when he comes back to work. We're like, look at this. We just made a new machine for you. It does all the work of the H and F machines combined. Not necessarily entirely. But nonetheless, so here's my H of F of X machine. Question, we've alluded to it already, but would that be the same as the F of H of X machine? Well, that would be taking H of X and replacing all of F's X's with its function. Okay? So that's cramming them in the reverse order. So what would that look like? Well, f of x was just blank plus 3, right? That was our plus 3 machine. And now I'm cramming, squeezing, crushing a square root of x inside of it. And that's equal to the square root of x plus 3, like that. So those are different machines that I end up with, depending on which order that I crammed them into each other. All right? So my question for you is, maybe that's a crazy one. Yeah, I think I'll avoid that question for now, because we might not be as familiar. Let me ask this question. What is the domain of the h of x machine?
That's range.
Oh, negative infinity to infinity.
So let's see. If h of x was equal to the square root of x, what's its domain? Can I plug in a 4? Could I plug in a 3?
That's a sad face.
Square root of 3 is okay. Yeah, right there. Square root of 3 is okay, right? Square root of 3 is a valid output. It's a real number. Could I plug in 1?
Yes.
Could I plug in pi?
Yes.
Square root of pi exists, yep. Could I plug in 0? Yes. Could I plug in negative 1?
No.
No. So what's the domain? It goes from 0 to positive infinity, right? Now the range is actually a little bit trickier on this, if I asked it. Now I'm only allowed to plug in positive numbers. What types of outputs do I get when I plug in only positive numbers? Could I get 0 out of this machine?
Yeah.
Square root of 0 is 0. Could I get 100 out of this machine? That'd be the square root of 10,000. Could I get pi out of this machine? I'd have to plug in pi squared. It turns out the range is actually going to be the same thing. Same thing. So, follow-up question. What is the domain and range? I'll just specifically ask domain because that's what's more interesting to me. Of h of f of x. So what did we say a moment ago that h of f of x was? That was the square root of the entire contents of x plus 3. Yep. So what's the domain of this going to be? Could I plug in 0? Yeah, I'd get the square root of 3. Could I plug in negative 1? Because I'd get the square root of 2. Could I plug in negative 3? Negative 3 plus 3 is 0. Square root of 0 is 0. Okay. Could I plug in negative 4?
No.
Well, if I plug in negative 4 for x, negative 4 plus 3 is negative 1. Square root of negative 1, as far as our functions are concerned, doesn't exist. So it doesn't like negative 4. In fact, whenever you see a square root, I know that the insides can't be negative, right? So if I'm trying to figure out domain, I might actually solve the equation. X plus 3 has to be greater than or equal to 0. And if I solve that, I'd get x is greater than or equal to negative 3. All right, so I know that the inside of a radical can't be negative. Can't be negative. Right? So you could actually solve that to help you figure out your domain sometimes. So my domain would be from negative 3 inclusive all the way up to positive infinity. All right, how about the range? Could I get a negative number out of this? No, because the square root of a positive number is always going to be positive. Yeah, it's going to be actually the same as the range from the previous one, oddly enough. Where for every input that I plug in from this domain, it's actually always going to give me a 0 or positive number, I guess. Or non-negative is the way I could describe that. So that's the idea there. Now, what I want to point out is earlier we had calculated h of f of negative 2, all right, or h of f of 6, and I plugged in the 6 for f and then took my answer, right, and plugged it in to h, right? Once I've crammed my machines together, I can actually calculate h of f of 6 rather easily. All right, so I could actually figure out h of f of 6. I could just use my h of f of x machine to do that for me, right? So that would just be the square root of 6 plus 3, all under the square root. So that's the square root of 9, which is 3. So I just want to point out, if you've calculated your machine, you can actually use your simplified version of it for good. Now, let's actually do one last example. Let's find j of f of x, and then evaluate j of f of 2, let's say. All right, so j of f of x, the j machine is the x squared machine, or the square machine. F of x is the x plus 3 machine. Which one's going into which? Right, f of x is going into j of x. So when I'm reading this function notation, all right, you kind of start at the innermost function and work your way out. So I'm going to be taking this machine and cramming it inside of the j of x machine. Right, so this would be my setup, except I'm actually taking this whole machine and just cramming it down inside there. So you work from the inside out, right? So start with this, plug it into j, is what that's saying. So let's figure this out. J of f of x, well, j of f of x is going to equal, the original j of x machine was just squaring stuff, and I'm replacing the contents of it with x plus 3. How do I simplify that? How did I do this? I used a pattern that we all have memorized, or you could have FOILed x plus 3 by itself, something to that effect. So there's my j of f of x machine. If I actually asked you the domain for that, all real numbers work. So negative infinity to positive infinity. If I asked you for the range, that would actually be a much tougher question in this case. Well, if it's in this form, not so much, I guess. You might be able to recognize that as a parabola in vertex form with a y coordinate of the vertex being 0. So that's, the range is actually 0 to infinity. Whereas if there was like a plus 1 on the outside, it would have been shifted up 1. But let's calculate j of f of 2. So to do that, I could have partially done it, or let's better yet just plug 2 into my composed machine here, my composition of functions. So that's going to be 4 plus 12 plus 9, 16 plus 9, oh, that's 25. Perfect squares right there. Bam, 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 bam. So, so that's what I end up getting. Now, it turns out there's actually another way to write that. J of f of 2 can also be rewritten as j little o f in brackets parentheses 2. And this is this little o is actually above the line there, and it's not an exponent, it's not a o, it's like a little circle multiplication dot equivalent. And this means exactly the same thing. This means j of f of 2. All right, is what that means. So that symbol is the symbol representing function composition when you're combining functions together. And I'll leave this for your homework. I think there will actually be some problems that might have you calculate h of f of h of x, where you'll have 3 things being composed, and you'll find the innermost one, the second innermost one, and then the third one as a result, and it all works out. So, thanks for watching, friends, and have a great day. Don't break company machines.